Hello everyone, welcome to ISF Week 9 interactive session. We will get started going through the summary of the topics discussed in the last week, and then we'll take up some problems from previous year as well as generic gate-related problems from paging, and we'll try to solve them. So let's get started. So basically, the week 9 lecture started is on memory management, how the operating system takes care of managing the main memory, different processes. So the majorly the topic discussed was on the major two types of memory allocation, basically contiguous memory allocation and non-contiguous memory allocation. So inside non-contiguous memory allocation, segmentation and paging was discussed. So before we get started, like why do we need, or when does the memory get allocated? So whenever, as we have seen in the process state, right? Whenever a process moves from new, make a transition from new to ready state, it means that the process is allocated memory and it is brought into the main memory so that the CPU can start executing the instruction. So this is where the memory management comes into picture, where which memory this process is being allocated and how is it taken care, how is this handled, all those things are dealt in the memory management section. So typically the program will be loaded into main memory, and then one by one the CPU will fetch the instruction and then execute the instruction. So typically for a program to execute, it must be in the main memory. That is what the CPU can actually access. Okay. So in between, so sometimes when the CPU is accessing the instruction one by one from the memory, a CPU can access both memory content from the main memory as well as from the register. So registers, since they are on the CPU chip itself, it will be much faster. It takes just clock cycle. But whereas memory loading will take couple of more clock cycle. So sometimes the CPU stalls so that the content arrives and then it can start working on that. So to reduce this memory stalls, typically something called cache is used. Which stores the frequently used items, and that will help reduce the memory stalls. Then another important aspect with respect to memory is memory management is to ensure the protection of memory space allocated to each process. So we can have multiple processes. P1, P2, P3, etc. P1, P2, P3, etc. allotted in the memory. So it should not P1, they all need to have their own set of memory. So if this is P1, P2, and P3, it should not happen that P1 will go and take content from P2's memory or P3 will take from P1. So these should not happen. P1 should be able to access only the contents from this designated memory. So these are ensured. This memory protection is actually ensured, and this is typically ensured using two registers known as the base register and limit register. Base register and limit register. So base register will tell from where this particular process memory is starting, and limit register will tell to which extent it can go. So base register will tell this is the starting of this memory for P1, and limit will tell this is where the memory ends. So if P1 try to access anything like limit +1, anything beyond its limit or the range, then there will be a trap or an error generated. So protection is ensured using base and limit registers. So in general, hardware support is provided to ensure that. So whenever the CPU gives an address, it first checks whether the address is within this base, and the address is greater than the base. So address for P1 should be within this range set. So address should be greater than base register, and address should be less than limit. So typically a limit will be the range. So it will be base plus limit. Base plus limit. Okay. So this is typically taken care by hardware address protection mechanism before the memory read is done. So this check is always done before we go for a memory read, so that none of the process reads any other process memory or data. Okay. So now when we are loading a process, so how is this address generated? Like how is it figured out? Okay, this is where it needs to be loaded and all that. So there are different ways of address binding, like binding the physical address to a program. So in some cases, it can be done in the compile time itself. Some cases it is done during the load time itself, and sometimes it is done using the execution time. So binding of instructions and data to memory address. And data to memory can happen either at compile time or at load time or at execution time. So when we say compile time, it means that when if we have written a program in C, when we do the compilation to generate the data, that time itself we know that this particular location in memory, which starts from 4983 some random value, we should know that this particular program is going to be loaded at this location. In that case, the compiled dotto will be having this absolute address here. I mean, we will know the absolute address where the program is going to be loaded, and then it will be loaded there. Okay. But in the one issue with this is that every time for the next time when we want to execute, if we change from this to some 598034, then again we need compile the program. So that this is how in case of compile time. So if we know the memory location a priori, the absolute code which can be directly put into the memory will be generated. Okay. In case of load time binding, here what happens is compiled code will always have a memory with starting from 0. Okay. So the compiled code will have the the instructions and aligned starting from 0. And when it is going to be placed on the memory, for example, if we are going to place it to a location 2539 or 50 something 8, then this all this following 0001, all the following addresses are added to this base address, and then it is um, put onto the memory. So that is when we don't know, if we don't know the memory location where we are going to put the program during the compile time, that's when we go for this load time binding. So this code that is generated is called as relocatable code. So all the addresses within this code is with respect to the start address of 0. Okay, so now this code can be put any to any location. Only thing we'll have to do is all the addresses should be added to that base address. So this is because it can be relocated to any location. It is called as a relocatable code. Okay. In case of execution time binding, here binding is delayed until the runtime. That is until the program actually starts executing. We are delaying the binding here. Okay, so these all these things requires hardware support to be needed. So this is how the binding can happen. So then, in general, when we look at the memory management or compiling a code that is available on the disk and then putting it onto the executing it, that is bringing it to main memory, um, there is always this concept of something called logical address and physical address. Okay, so physical address is the actual memory address. Memory address is the actual memory address. We call it as physical address. For example, we have like if we have 2 GB of RAM, 2 GB of RAM, it will start and it will go to till that endpoint, right? So this full memory is the physical memory, and the address of each byte in this memory forms the physical address. Okay, but in case for if we take this particular program, we are getting some addresses here, right? So the addresses that that the CPU generates for each program is called as the logical address. Okay, so this logical address and physical address will be different, and then we map the logical address to the physical address. So logical address is not the actual memory address. So for every process or every program, for every instruction, we'll have a logical address which is generated by the CPU. Then this particular logical address will be mapped to a physical address, and then during the execution, the instruction will be then further retrieved from that location, and then it will be executed. Okay, so so always there is this two concepts that comes in whenever we talk about memory management. That is one is the physical address, and the other is logical address. And memory management unit typically helps convert this logical address to physical address and retrieve the content from the physical address. Okay. So then there is, the also the concepts of dynamic loading and linking was also discussed. This dynamic loading is nothing but it allows a routine to be loaded into the memory only when it is used. So we delay it until and unless actually that particular function or the code is used during the process. invocation. Then coming back to contiguous allocation. So as I said, this is the memory available, the RAM memory available. One can either get a contiguous chunk of space in this memory, and then we can directly load the program here. This is one way of having, this is called as contiguous memory allocation. So all the instruction in this program will be available in continuous location. Okay, continuous memory location. Another approach is non-contiguous memory location. So in such non-contiguous allocation, we divide the programs into something called pages or blocks, and then one block can be placed here, the other block can be placed at a different location, third block can be placed at a third location. So this is what is non-contiguous allocation. Instead of having the whole program loaded onto a continuous memory location, we split the whole program to multiple blocks, and each of these blocks can be put into different locations in the memory, and then we track where each block is kept. So that is the non-contiguous memory allocation. So in case of contiguous allocation, in the very initial time, and there was mainly main memory, it was divided into two partitions. Typically one for loading the operating system and the other for loading the processor. So if we can typically it is divided into starting from 0 to the max value, right? So the this portion is normally used for loading the operating system, the interrupt vectors and all, and the lower portion is used for allotting processes and all that. With respect to contiguous allocation. So with continuous allocation, as we discussed initially, we will always have the base relocation register plus the limit register, which takes care of ensuring the protection whenever the program is accessing any location. Okay. Then this was one type of partitioning. Another partitioning was to partition the memory into fixed size blocks. So this whole memory will be partitioned to fixed size block, and then programs P1 will be given this block, P2 could be given this block, P3 could be given this block. This was one approach. Another approach was to have variable size partition. So this could be larger partition, this is smaller one, this is very smaller one, and this is kind of medium in this way. So based on the size of the program, one can allot the memory accordingly. So one of the major issues with these approach as contiguous allocation is the we'll come to the concept of external fragmentation. So with this fixed and variable size memory locations, we will allot different programs to different blocks. Okay, so there are some methods for allotting these programs into these blocks. So one approach is to what is known as first fit approach, second is best fit approach, and third is worst fit approach. That is, in first fit approach means if P1 is coming, P1 will check which block is free. This is free, and whichever is the first free block that can accommodate P1, it will go and occupy that block. Then the second, again, same P2 will come. If, for example, if this was already occupied, P2 will come and P2 then occupies this. So like this, one by one, in the first come in this order, they will check the availability and occupy that. That is the first fit. In the best fit approach, what happens is P1 will come and look all the, for example, if P1 is like 4 MB and this was like 10 MB, this was already occupied. P2 is occupied here, 4 MB, and this is, let us, this is 9 MB, P2 was 6 MB, and P2 is 5 MB. And this is 4 MB and this is 5 MB. Now P3 is 4.5 MB. Now what happens is P3 will come and see which are the, this is occupied, this is occupied, these two are the free available. So it will see which is the smallest hole that will fit in. So both for, sorry, it should be 3.5. 3 MB. So, which is the smallest hole that will occupy, whether it is 4 MB or 5 MB. So, it will go and occupy this block, which would fit it properly. Okay, so okay, let it be 3 point. Okay, and so this is how best fit work. Whereas in worst fit scenario, it will go and occupy the largest available block. Every process will be allotted to the largest available block. And based on that, so whenever we do this variable partitioning, the problem with these approaches are here, like P1 was 9 MB only, but this block is 10 MB. So 1 MB is actually free, which is not used by anybody. Here P2 is 5 MB, whereas we have given 6 MB place. Here again there is memory that cannot be used by anyone, right? So these are the main issue with such kind of allocation. This amount of memory within a block that is being not used is called as internal fragmentation. Okay. Now, let's take an example and see how this first fit, and let's look at an example before we move to the next this one. Assume that we have three processes, P1, P2. Yeah, we have four processes, P1, P2, P3, and P4, with process sizes 90, 50 MB or KB, 30 KB, and 40 KB. And assume that we have 5 blocks in the memory. We have 5 blocks in the memory. Block 1, block 2, block 1 is 20, block this is 100, this is 40, block 3, this is 200, and this is 10. So in case of, let's see how first fit will work here. So here the 90 P1 will go and check first 120, it cannot fit in. Then it will check 100, yeah, it can fit into 100, right? So P1 will occupy 100. P1 will occupy 100. Now P2 will come. P2 will see, okay, 20, P2 cannot occupy. 40, it is not sufficient for P2. But 200, it is sufficient. So for it will take the first available hole or block where the process can fit in. So here P2 will occupy. Now P3 will come. P3 will see 20 and 40. 40 is good enough for P3. P3 will occupy 40. Now P4 will come, but P4 in the available free ones are only 20 and 10. So this will remain unallocated until one of these processes move off. Okay. So this is one example of first fit. Another example of probably, let's take the second example of best fit example. Yeah, with P1 size 40, P2 with size 10, P3 with size 30, and P4 with size 60. And the blocks are 100, 50. These are the memory blocks. 30, 120, and 35. So, so now in case of in case of best fit, P1 will is 40, so it will check, it will actually scan all the available and choose the one which is best fitting 40. So if you see here, 100 will fit, 50 will fit, 120. In all these three places, P1 can occupy, but P1, since this is best case scenario, P1 will choose this block. B1, B2, B3, B4, and B5. So this will be chosen by P1. Now P2 requires 10. Okay. So we have 100, 30, 120, and 35. So of the available, which is the best fitting one? Best fitting one is 30. So P2 will occupy this. Now P3 is 30. So there is 100. P3 can occupy 100, 120, or 35. So then since this is best fit, P3 will be occupying this. Now P4 will have 100 and 120. So P4 will occupy 100. So this is how best fit strategy works. So if we see the same, if we try how it will be for the first fit, 100, 50, 30, 120, and 35. This is best fit. If it is first fit, P1 will come, P1 will occupy 100. P2 will come, P2 will occupy 50. P3 will come, P3 will occupy 30. And then this will remains, P4 will occupy. So in case of first fit strategy, what the free block that would be available is of 35 KB, whereas in case of best fit, 120 KB will be available. Let's see if worst fit, how it will be on the same block. Let's see how the worst fit will work. 100, 50, 30, 120, and 35. So in case of worst fit, we take the largest one available. Okay. So here we have P1 will come, P1 will occupy the largest hole or block that is available. So 120 will be occupied. Then P2 will come, P2 will come and occupy, though it needs only 10, it will take the next largest one. P3 will come, P3 will take the next largest one. And then unfortunately P4 there is no space, P4 cannot fit in 30 and 35, and thus P4 will remain unallocated. So hope with this example it is kind of clear, these three strategies. Then now let's see what is the other topics discussed. Yeah, the other topic discussed was basically with the concepts of internal and external fragmentation. Okay. So internal fragmentation is like when you allot a particular block to a particular process. For example, here P2 required only 40, but we have given 100, right? But of the 60 is not used. But since this is the block this 60 remains unused and nobody else can use it. So this is called internal fragmentation. External fragmentation will come when, like now here we have 30 and we have 35. These blocks are being unusable, right? Because there are holes scattered across. So this forms the external fragmentation. So to fix external fragmentation, we use what is called compaction. So we'll remove this P1 to this here and 330 to here, so that a bigger chunk of 75 comes to the towards the end of the whole memory, and then this 75 can then be allocated to any process. Okay, so that is, and what, and then now going back to this comes with respect to contiguous allocation. Now, non-contiguous allocation, the two topics discussed was segmentation and paging. One is segmentation, the other concept is paging. So then, and the third one is page segmentation. Probably sir will be discussing it in the next class. So in segmentation, we typically divide the process, the program into different segments. Like a big program will be divided into different segments, small segments, and then these segments will be allotted. These segments will be given in the memory. This will be one segment. This will go to the other segment like this. The program is split into different. So here, if you observe here, we are not trying to keep this whole program in a big chunk of memory. So we are splitting the program into smaller chunks, and each of this chunk is going to a smaller chunk of memory. So it's not like this whole one block is, that was with contiguous allocation. So here we actually split the logical address place into small unit, and we try to allocate each of these to smaller blocks in the memory. And then this where the segment is given, where the segment is mapped, where this is mapped, all these are tracked using what is known as a segment table. Okay, so that is taken care using hardware support, and this if we give some numbers, segment 0, segment 1, segment 2, segment 3, segment 4, we have given here segment 0 is there, right? Then this is where segment 3 is kept, and this is where segment 4 is kept. So it's not a, in the physical memory, these segments can be scattered, and when the CPU processes the instruction one by one, the logical address, that is the segment number plus offset within the segment, there will be an offset for each of the instruction. So the segment number plus offset will be translated into this physical memory. So that is how segmentation works. So as I said, the logical address will be split into segment number, comma, offset. Okay, then this information will be available in the segment table, and we also use what is known as base and limit to ensure that each process access only its segments, and within that limit it doesn't access the segment of other processes. Okay, so that is quick summary on segment. Now the next topic that was discussed was paging, or probably maybe before going to segmentation. Paging, we can have a small example on segmentation. Simple example we can try, and then yeah, so let's see this example. there is this table given here. This is segment number. Then we have base and limit. Segment 0, the base address is 1219 and length is 700. Segment 1 is 2300 is the base and 14. Okay. Segment 2, 90, 100, 3, 1327, 580 and 41952 and 96. Okay. So the question here is which of the following logical address will generate a trap, and if there is no trap, calculate the physical address. So let's first calculate the physical address. Okay, so let's calculate the physical address for the following, that is logical addresses. Physical address for given logical address. One is 0,430, the other is 1,11, 2,100, 3,425 and 4,95. Okay, so if we see here, how do we compute the physical address? It will be for the segment, we know what is the base, right? For segment 0, the base address is 1219. And this is the offset within that particular segment. So physical address will be the base corresponding to 0. This is the base address. So it implies that okay, so if you see this as the physical memory, there is this 1219, this is segment 0, which is starting with 1219, and this whole length or the limit is 700. Now another thing, if you see 2300 is the starting address for segment 1, and its whole length is, it's only 40. This is segment 1. Okay, so this is how it will be on the in the memory. So when I say when we say segment 0, yeah, the memory, physical memory will start with address 1219 and the offset. So within this, the offset is 430. So 1219, 1, 2, 3, 4, we have to see, and this will be the location that we want to ask, which is 430 from here. If it is 0, this is 4. So the physical address will be 1219 plus 430. Okay, which is 9461 1649. Now, before computing this, the for the protection, we will also check if this offset 430 is less than the limit. So the limit for when we give the limit, it will be valid address will be 0 to limit minus 1. Limit minus 1. Okay. So 0 to 699 is the valid for segment 0. 430 is less than 700. So this is the physical address. So there won't be any trap generated. Now for this one, 1,11, the base is 2300 plus what is the limit is 14. Okay, 11 is less than 14, which is true. So we added. So 2311 will be the physical address. Now for 2,100, for 2,100, the base is 90, this one. But if we see here, the offset is 100. 100 is less than 100. No, right? The valid range is only 0 to 99. So 100 have crossed the limit. So this will, we cannot generate the physical address, and this will create a trap. Okay. Then in the next one is 3,425. 3,425. Here the base is 1327 plus 425. 425 is less than or equal to 580 minus 1, which is 579. Right? Correct. So we will add this up 425 and we will get 1755 as the physical address. Now 4,95, 4,95. The 4 for segment 4, the base address is 1952. Then we have to check whether 95 is less than or equal to 95. 96 is the limit. So 95 is less than or equal to 95, right? So we can access. So when we say 96 is the limit, 0 to 95 is what we can access. 0 to 579 is what we can access. Here, 0 to 99 is what we can access. 0 to 13 and similar way 0 to 699. So here, yeah, this is valid. So we add it. 2047 will be the physical address. So this is how the base and limit register takes care of the protection mechanism. Now let's go to paging. So in paging, here the concept is that both the we divide both the logical address space and logical and physical address is divided to what is known as pages. Pages. Okay, so assume that we have a large program and we have little memory. Okay, so we divide.
Ma'am.
Yeah. Yeah, tell me.
Ma'am, some lines speaking something in Hindi, please. But
I'm not
I don't
comfortable with Hindi.
protect the
I'm not that comfortable with Hindi.
Okay, ma'am.
Yeah,
Okay,
and
ma'am.
I'm really sorry. I can understand Hindi to some
Okay,
extent.
ma'am.
I can
I try.
converse,
I try.
but
Okay, ma'am.
yeah,
I
but
try.
my Hindi won't be that good to be recorded and put it in
Okay, ma'am.
uploaded
I
and
try.
all
And
that.
thank you. Thank
Yeah, 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 yeah. I'm sorry. So in case of this is a logical address space and this is a physical address space. Here both the logical address and the physical address is divided to what is known as equal size pages. Okay, so this size and this size will be same. This is same. Okay, so whenever when we divide this logical address space into pages, we take one page. So how we map the memories? Take this one page and put it to the physical address. Then we track in logical address space term. We call what is known as pages. And here these 1, 2, 3. This is called as frames. Here 1, 2, 3, 4, 5. These 5 are called as pages. Here they are called as frames. Okay. So but the size of the frame and the page will be same. So this location we can go and put it here. So where we are going to map how the pages, so we call each of these as a pages, how the pages are mapped down to the frames are tracked in what is known as the page table. Okay. So here, so in paging, there are a couple of things coming like the this I'll come to it and we'll see a couple of examples also. Okay, how this address mapping, how the page number to frame number mapping is done, and all that. Okay, so in paging, this is the basic concept. You divide the logical address space and the physical address space to equal size blocks or chunks called pages. Then you map the pages to frames. So wherever you are allotting this particular page on the physical memory, that particular mapping of page number to frame number is tracked in what is known as a page table. And then using that page table mapping, the physical memory will be retrieved. Okay. So how it happens is there is this logical address space, we divide it into what is known as this is page number plus offset or displacement. So as you can see, this offset, since we are dividing it into equal size pages, both the physical and the logical memory, this offset here, here, this offset and the corresponding offset in the frame will also be the same. Okay, but the page number will be mapped to the respective frame number. So how this works is we divide the logical address into what is known as page number and offset. Then we once this is done, there is something called as a page table. So page table will have entries which will tell us the mapping between the pages to the frame. So this will have frame numbers F1, F2, F3, etc. Okay. So we will go look up here. Whatever is the frame number written here, this will be retrieved and then it will become F plus D. And this forms the physical address. And using this physical address, we access the memory, physical memory. Okay, so this is, so a page number will contain the mapping of the page to frame. Okay, so we have these are frames. So in this frame, this will be the offset. So this frame plus offset will give the physical address. Okay, so now let us take some examples and see some, yeah, let me just down some example questions. Yeah. So let's see, given given a size of memory, calculate the size of memory if its address consists of 22 bits and memory is 2-byte addressable. Okay, so that is calculate size of memory if address consists of 22 bits and 2-byte addressable. So what does 2-byte addressable means? That two locations are addressed using two bytes will have one address. Okay. So in all the earlier examples and all, we were considering single byte addressable. So here 2-byte addressable means, if let's assume this as byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, byte 7, byte 8, byte 9, byte 10. This 2 bytes will be addressed by 0. This 2 will be addressed by 1. This 2 will be addressed by 2. Like this. Okay. So this is what 2-byte addressable means. So one address will represent 2 bytes. Okay. So okay, so it's told that the address consists of 22 bits. So with 22 bits, how many different numbers or locations we can address? Take the simple example of in binary. I hope these are you all are aware of this. For example, if you take a 2-bit number, that is 2 bits are there. So the combinations are 0, 0, 0, 1, 1, 0 and 1, 1, right? If we take 3 bits, like bit 0, bit 1, bit 2, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1101111, right? So when we have 3 bits, what are the different addresses or addresses that we can get? We can get 2 power 3 different addresses, right? Hope this is clear. 1, 2, 3, 4, 5, 6, 7, 8. Same way, if we have 2 bits, we can have, this is actually decimal 0, 1, 2, and 3. This is decimal 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so based on the number of bits, if we have n bits, we can have 2 power n different addresses. So here it is given that we have 22 bits. So which means that we can have 2 power 22 different addresses. In addition to that, it is also told that each of this address will correspond to 2 bytes. So it is not 2 power 22, it will be 2 power 22 into 2 bytes. So size of the memory will be 2 power 22 into 2 bytes. So with 22 bits, we can address 2 power 22 different locations, right? And each of this location is of size 2 bytes. So the total memory size of the memory is 2 power 22 into 2, which is 2 power 23, which is 8 MB. So normally in this calculation, we take 2 power 10 as K, 2 power 20 as M, 2 power 30 as G. Okay, so it is actually 2 power 3 into 2 power 20. So 8 into MB. So this is how. So hope this translation is clear. Like n bits, if we have, we can have 2 power n different. We can address 2 power n different locations. Hope that is clear. Now the next question is. So if we have a memory of size 16 GB and it is 4-byte addressable, calculate the number of bits required in the address. Okay. So we have memory equal to 16 GB. Then we have the memory is 4-byte addressable. So what it is asking is calculate number of bits required in the address. Okay. What is the So let's assume it as single byte addressing. Let me not confuse. Number of bits. What is the number of bits needed to address? So we have 16 GB. Okay. So every byte needs one address, right? So it is 1 byte addressable. So every byte needs one address. So in 16 GB is equal to 2 power 4 into 2 power 30, right? 2 power 4 is 60 and 2 power 30 is giga, which implies 2 power 34. So if we need to address 2 power 34 locations, we need 34 bits. Okay, so the number of bits required is 2 power 34. Now, now if it was 4-byte addressable, then number of locations that we need to address will be 60 GB by 4. Okay, so it is equivalent of assuming that your page is of 4 bytes. Okay, so 16 by 4 is 4. That is 2 power 2 into, which is equal to, into 2 power 30, which implies 32 bits. Okay, so that was one. I mean, I got this problems online only. Just kept this so that you become familiar with this with manipulations. Okay, now the next one. Consider a system with 32-bit logical address. Logical address is 32-bit. Are you having any doubts? Any doubts? Okay, I'll continue. So logical address is given as 32 bits and page size is given as 4 kilobytes. Page table entry. Entry size. Each page table entry size is 4 bytes. Now, what is the size of the page table? Okay. So assume this is the page table we have. Okay. We don't know how many entries are there. We don't know how many entries are there. How many entries are there? We don't know. But we know what is the size of each of these entry. It is given as 4 bytes. Okay. So, so what will be the size of the page table? So each entry is 4 byte. And if we assume that there are n entries, so n into 4 bytes, right? So now how can we find out this n? So we will find out this n using the logical address bits and the page size of the page. Okay. Page size is 4 kilobytes, which is equal to 4 kilobytes equal to 2 power 2 into 2 power 10, which is 2 power 12. Okay. Then we have 32-bit logical address. So we know logical address is P and D, right? So to represent the offset, The page size is 4 KB. So to represent 4 KB, we need 12 bits. B is equal to 12 bits. This total is 32, right? So how much will be P? So P is equal to 32 minus 12, which is 10, sorry, 20. Okay. So with 20 bits, we can have 2 power 20 different pages. We can address 2 power 20 different pages. So n is 2 power 20. So the size of the page table will be 2 power 20 into 4, which is 2 power 22, which is again equal to 4 MB. Okay. So this derivation, is this clear? Like when we tell that 32-bit is the logical address, this comprise of the page, the number of bits required address the page table plus the number of bits required to address within the page. Okay, the offset within the page. Okay, so when we say the page side pages of 2 power 12, that is it will start from 0 and this address will be 2 power 12. What will be that value? 2096, I think, or 4094. 4094, I think. Okay, from 0 to this much. Okay, so now that is represented using 2 power 12. So we are using 12 bits, and using 12 bits, we have this many individual, we can address it. So this 12 bits of the logical address will be used to identify the offset within the page. So within the page, the displacement or the offset. Okay. Now we have what is known as page number, which will help us identify the frame. Okay. So this is also represented using some number of bits. So how many total? It is given that we have 32 bits. Of the 32, 12 bits are used for representing the offset or displacement within the page. Okay, so the remaining 20 bits are used to represent the number of pages available. So if we have 20 bits available, we can represent 2 power 20 different pages. Like as I said, if we have 2 bits available, we can represent 2 power 2 4 different pages. Same way, if I have 3 bits available, I can have 2 power 3, that is 8 different pages. So if we have 2 power 20 bits available, we can have 2 power 20 different pages, and thus the size of the page table is, as we have seen, it is n into 4. So n we have got it as 2 power 20, and thus the answer is 4 MB. Okay. Now the next problem. Consider a machine with 64 MB physical memory. So here physical memory is 64 MB and logical address space is 32 bits. 32 bits. Page sizes 4K. 4KB. What is the approximate size of the page table? Okay. So here we are given physical memory 64 MB, logical address space 32 bit, page size, page size as 4 KB. So here both the parameters are not given, right? So what is the size of the page table? It will be size of each of these entry, size of this, that is x plus this, that is n, right? So n into n into x. Both are not given, right? In the earlier question, x was given. We found out n and then we figured it out, right? So here we are told that physical memory is 64 megabytes. So let us put it in terms of 64 is to power 6. To power 6 into m is to power 20. Okay, which is to power 26. Logic, this will be 2 square into 2 power 10, which is 2 power 12. Right. So the number of pages will be 2 power, sorry, 32 minus 12, which is 20. So 2 power 20. Okay. So what will be the size of each of this entry? So that we have to find from 2 power 26. Okay. So like logical address, this is logical address. We know the displacement is 12 and this is 20, total 32. Now the physical address total is 26. 26. We know this is 12 because the page size is same. Frame size and page size is the same. So what will be 26 minus 12 is 16. How much is 26 minus 12? This is 14, right? Yeah. So this is now 14. So in the page table, every entry, this entry will be 14 bytes. So n is 2 power 20 and x is 40. Okay. So 2 power 20 into 40. So why they are asked, since they have asked to find the approximate, we can put this as 2 power 20 into 16, which will be 2 power 20 into 2 power 4, which is 2 power 24, which is 16 MB. Okay. So that is okay. Oh, no, I can't write it as MB because this is bits, right? 1 second. So this is 2 power yeah. So this is 16 into 16. This 16 is bits. So it will be 2 power 20 into how many bytes? 2, which is 2 power 22, which is 4 MB. Okay, so that we have to be little careful while doing that. Okay. Yeah. Oh, sorry, it is 2 MB. The power 1, right? 421, which is 2 MB. So this is one question. Let's take one more, probably. Fine. Let's see one more question. Then we will go back to the previous year questions. So in a virtual memory system, size of virtual address is 32-bit. Virtual address is nothing but logical address. Logical address is 32 bits. And physical address is 30 bits. Page size is 4 KB. And each page table entry is 32-bit. Size of each page table entry. Bit. Okay. So the question is X number of bits that can be used for storing other information in the page table entry. So there are other information also that gets stored in the page table, okay, which I think will be discussed in the next class. But we will just take a look at this problem. When we try to equate this, we will see that there are some additional bits available which can be used for storing some other informations. We'll just take a look at it, okay, quickly. Okay, so let's convert this to power 12. Okay, so we have logical address as 32 bits, and this is 30 bits. So this is 30, this is 32. So we have 12 and 20. This again 12 and 18. Right? Yeah. So it is told that so in the page table till now we have seen that this size of this entry is same as this one, the frame, the number of bits in the F, right? It is same as F, or it is 18 is what we have been seeing in all the examples, but here it is given that this is 32. This is 32. Okay, but we actually, to address the frames, we actually need only 18, right? So, but it is given that there are 32 bits. So 32 is given, the size of the page table entry is given as 32. Whereas to address the physical memory or to compute the physical memory address, we need only 18 bits. So 32 minus 18 is 14. So 14 bits are available for additional information. So the what I was trying to do with this problem was to map the bit information to the address space. in both the physical and logical address space. So it's good if you get familiar with this mapping and then figure out how many bits would be needed for addressing and like that. Okay. Yeah, so with this kind of the generic questions in PG. Now let's go back to the previous year questions. Okay, I'll share the screen. So the first question, so these are the like paging questions that I discussed. I have just kept it in the first slide. The other examples I did not keep. So these are the problems we just saw. Okay. I took it from this side. So question one, which of the following statements regarding a segment table is incorrect? Okay. So segment table BR is the base register. This points to the segment table's location in memory. So yeah, segment table BR points to segment table's location in memory. That is true. Base contains the starting physical address where a segment reside in memory. That is also true. STLR is the length register. It indicates the number of segments used by a program. And then the other one is segment number S is legal if S is greater than STLR. So that is the S is legal if S is less than STLR. But here it is given as S is greater than STLR. So option D is wrong here. Rest all the statements are correct. So segment number S is legal if S is greater than STLR. Okay. So the question, second question, the reason why the CPU has to stall occasionally is the reason why the CPU has to stall occasionally is the processor might not have enough data to carry out the instruction. Since access to the register may take many CPU clock cycles, memory access may take multiple CPU clocks, and the processor might not have the data required to complete the instruction execution. The next is B. Access to cache may not be allowed for several clock cycles, thus the processor might lack data for execution, and C, none of the above. So can you type in your answers which you think is right? Then we can discuss. Or you can unmute and speak as well. So why does the processor need to stall in between? Is it because reading the register takes more CPU cycle? Actually, register read doesn't take, it takes only one CPU cycle. So that is the thing. Cache is also does not take multiple CPU cycles. So here the answer is actually B, because memory access, as we've seen, memory access takes multiple cycles. So by though the CPU will initiate a memory read, but in the next clock cycle, the information will not be available to be processed or act upon. So that because information, the red information is not available for the CPU to proceed with the next instruction processing. The CPU normally have to stall when there is memory access. So the answer here is B actually. Yeah. So the next question, which of the following techniques is used to secure memory? So one user process cannot access the memory of another user process. Yeah, that is true. Then a base register and a limit register define the boundary of a program in memory. So, yeah, base and limit registers are used to ensure safety. Then the third one is CPU must check that every memory access generated in user mode is restricted within base and base plus some limit for that. That is also true. So the all of these are used to ensure security, like memory is not accessed, memory of another process is not there just by another. Okay, so all these techniques are used, and this the answer is all of the above. The the next one is which of the following claims about external fragmentation is true. So compaction is possible only when I/O is in progress involving memory that is being compacted. Compaction is not possible if relocation is dynamic and is done at execution time. The memory contents are shuffled to place all the free memory together in one large block. None of the above. So here for a change, they have asked which of the following statement is true. Normally all the question will be which of the following statement is false. This time it's about true. So if you see the memory content are shuffled, option C, memory contents are shuffled to place all the free memory together in one large block is actually bot compaction. That's okay. So that is the answer here. Answer is C. The next question. In dynamic linking, stub is used for locating the appropriate memory resident library routine. Dynamic linking can be postponed until the execution time. Then operating system checks if routine is in process memory address, and if not the address space, then it is added to the address space. So stub is actually used for locating the address appropriate memory resident library routine in case of dynamic linking. That is done actually. So, and it can be, yeah, that is what dynamic linking is, postponed until execution time. And yes, it checks. So all of these above, all of the given answers are correct here. Yeah, so the next question, next question is map the following columns: a symbolic address, absolute address, and relocatable address. Absolute address is actually the physical address, so it is available with the linker or the loader. Okay, so Q and W matches. Okay. Then relocatable address is the one that the compiler normally generate when it doesn't know where we are going to put the program. So compiler generates the relocatable address. So R is mapped to U. Okay. And so R is mapped to U. Q is mapped to W. The symbolic address is the one in the source program. So the option here is C. The answer here that matches this is C. Okay. Symbolic address is the one in the source program. Absolute address is the one, the final physical address wherein we'll be loading the program. Relocatable address is the one generated by the compiler. Okay. Now next question. Which of the below statements is false? So absolute code can be created at compile time when a memory location is known, but it must be recompiled each time the beginning point changes. Yes. So absolute code can be created at compile time if we know where we are going to place the program. Okay. But the difficulty is that we have to compile every time the address changes, it has to be compiled. So A is true. If hardware support is unavailable at load time and memory location is unknown at compile time, relocatable code must be produced. Yes, yeah. When we don't know the memory location at compile time, then yes, we need to generate relocatable code. That's also true. Sorry. Next, if the process may be transferred while it is running from one memory segment to another, binding is postponed until runtime. Yes, if the process while it is running from one memory segment to another, binding is postponed until runtime. Yeah, that is also true. So here none of the statements are false. So the answer here is none of the above. So now the next question. Between logical and physical address, both are generated by memory management unit. Both are generated by CPU. MMU generate logical address while CPU generate physical address. And MMU creates physical address, CPU creates logical. So this is the correct statement. Memory management unit creates a physical address, whereas CPU is the one that creates the logical address. So the answer is D here. So now the next question. In a hierarchical paging policy, there are 4 hierarchical pages. We can skip this because this is not handled in the class, right? So let's skip this question. Hierarchical paging comes, I think sir will cover it in the upcoming lectures next in upcoming week. So which of the below statements is false? Depending on the value of the program counter, the CPU fetches instruction from main memory. Yeah, that is true. The memory of another user process cannot be accessed by another user process. Yeah, memory it is protected. One process cannot access the memory of the other. So that is also true. So yeah, so this is also true. It is true. Now, memory unit only sees a stream of address and read request or address data and write request. Yes, that is also true. Memory unit keeps track of how address were generated. No, memory unit does not keep track of how the address were generated. So the statement is false. It keeps track of how address is generated as the false statement here. Okay. And so with this, we complete the previous year questions also. So I can take any doubts or in case, uh, like, if you want, I can try explaining in Hindi, but I'm not sure how good it will be. If you are okay to bear some mistakes and other things, I can mix Hindi and English and try explaining. Sajay Balam, you were asking, right? Which topic you want me to discuss? In specific topic or all the way from starting? Yeah. So I'll share the other so FCFS FCFS का फुल फॉर्म है फर्स्ट कम फर्स्ट सर्व। ओके, ये एक स्केड्यूलिंग एल्गोरिदम है। ये यूज करके सीपीयू को लाइक जो भी प्रोसेसेस वेटिंग रेडी क्यू में वेट करते होंगे ना, तो ये स्केड्यूलिंग एल्गोरिदम यूज करके we give the CPU to each of these processes.
Okay,
Is this what you are referring to? FCFS CPU scheduling policy है ना। तो समझो कि ये एक रेडी क्यू है, इसमें P1 P2
P1 P2 कुछ प्रोसेस
P3
एंड प्रोसेस।
PN एक्सेट्रा है इसमें। तो
ओके
यहाँ पे P1 पहले जिस ऑर्डर में वो लोग क्यू में आते हैं उसके हिसाब से स्केड्यूल होता है। ठीक है, जो
ओके
पहले आता है उसको पहले सीपीयू मिलेंगे, जो सेकंड आता है उसको सेकंड मिलेंगे। इफ सपोज एट टाइम जीरो, अराइवल टाइम सबका जीरो ही है, लेकिन इस ऑर्डर में आया है P2 P3 P4, py, ये अराइवल टाइम है, ये प्रोसेस है। अराइवल टाइम 0th टाइम पे इस ऑर्डर में दे ऑल हैव कम, तो
अच्छा।
इसी ऑर्डर में उनको सीपीयू भी दिया जाएगा। मतलब P1 को पहले देंगे, उसके बाद P2 को देंगे, उसके बाद P3, उसके बाद P4 एंड उसके बाद P5। सो यही है FCFS का फंडा।
अच्छा, बस टाइम मैम,
क्या?
बस टाइम, BURST, बस टाइम।
बर्स्ट टाइम,
यस।
बर्स्ट टाइम मतलब कितना टाइम सीपीयू यूज करेंगे। मतलब
जो
एक
कंज्यूम।
एक बार दे दिया ना, अभी मैं बोल रही हूँ कि P1 को सीपीयू दे देंगे। यदि एक मिनट मैं ड्रॉ करती हूँ। यदि P1 का बर्स्ट टाइम है 10, इसका 20 है, इसका 5 है, इसका मतलब 30 है और इसका 60 है, तो उसका क्या मतलब है कि P1 को जब हम सीपीयू देंगे तो वो 10 टाइम यूनिट्स के लिए सीपीयू यूज करके इट विल गिव इट बैक, इट विल रिलीज इट। ठीक है, 10 टाइम यूनिट, वो मिली सेकेंड हो सकता है, माइक्रो सेकेंड हो सकता है। ओके, 10 यूनिट ऑफ टाइम के लिए यूज करके इट विल रिलीज। और FCFS इज अ नॉन प्रिएम्प्टिव शेड्यूलिंग, इसमें प्रिएम्पशन नहीं होता, प्रोसेस को खुद 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 सीपीयू रिलीज करते हैं।
ओके।
ठीक है, यदि P1 को सीपीयू दिया है तो P1 विल एग्जीक्यूट, जितना टाइम उसको एग्जीक्यूट करना है उतना टाइम एग्जीक्यूट करेंगे अंटिल वो कंप्लीट करेंगे, या कुछ आईओ के लिए जाएंगे। कुछ आईओ के लिए जाएंगे तो वो ब्लॉक हो जाएगा रन, तो दूसरे प्रोसेस को सीपीयू मिलेंगे।
ओके मैम।
ये लेट मी कंप्लीट दिस। तो ये यहाँ पे क्या होगा, 10 टाइम यूनिट्स के लिए P1 एग्जीक्यूट करने के बाद इट विल रिलीज द सीपीयू। उसके बाद P2 को मिलेंगे सीपीयू, P2 भी 20 मिनट के लिए एग्जीक्यूट करेंगे, फिर एंड इट विल रिलीज इट। फिर P3 को मिलेंगे तो P3 विल एग्जीक्यूट फॉर 5 टाइम यूनिट्स, एंड आफ्टर दैट P4 को 30 दे देंगे, P4 विल एग्जीक्यूट फॉर 30 टाइम यूनिट्स। उसके बाद P4 विल रिलीज द सीपीयू, then P5 will get and it will execute for 60। ठीक है, तो दिस इज दी। सो इसको हम यदि गंट चार्ट के रूप में इफ वी रिप्रेजेंट इट, सो दिस इज 10,
20।
this is 20, this will be 5, this will be 30 and this will be 60। so waiting time for P1 will be 0, for P2 P1 P2 P3, P1 का वेटिंग टाइम 0 है, P2 का 10, P3 का 30, P4 का 35, 65। So this is how we compute it। ठीक है,
ओके मैम।
ठीक है। और कुछ टॉपिक्स है ऐसे, मतलब आई कैन ट्राई एक्सप्लेनिंग इन हाउ आई जस्ट डिड, मिक्सिंग अप इंग्लिश एंड हिंदी।
वेट मैम। नो मैम, थैंक यू।
ओके, ठीक है।
वेट, मैं दिस नोट, ये इसको नोट कर लेते हैं पे। वेट, एम फुल फॉर्म इसका क्या हो सकता है, FCFS का?
फर्स्ट कम फर्स्ट सर्व।
फर्स्ट का फर्स्ट का P1 P2। ओके मैम, कंप्लीट। मैम,
यस,
इंटरप्टेड का मतलब क्या होता है, इंटरप्टेड?
इंटरप्टेड मतलब जब ये प्रोसेस शेड्यूलिंग के कॉन्टेक्स्ट में पूछ रहे हो क्या?
ओके।
नहीं, मैं इंटरप्टेड का मतलब यू आर आस्किंग इट इन द कॉन्टेक्स्ट ऑफ प्रोसेस शेड्यूलिंग। इंटरप्ट करना मतलब रोकना, और
अच्छा, वो उसको आई थिंक ब्रेक ना, रोकना, रुकावट डालना।
हाँ, यदि प्रिएम्प्टिव
मतलब
शेड्यूलिंग में कैसे होता है कि अभी नॉन प्रिएम्प्टिव है तो इसमें P1 या P2 खुद ब खुद सीपीयू को रिलीज करते हैं। यदि नॉन प्रिएम्प्टिव है तो द scheduler will stop and interrupt and take the CPU back. शेड्यूलर रोक के सीपीयू वापस ले लेते हैं। लाइक फॉर एग्जांपल राउंड रॉबिन शेड्यूलिंग पता है?
राउंड रॉबिन नहीं में।
सो राउंड रॉबिन एक शेड्यूलिंग स्कीम है।
ओके, राउंड
इट्स अ
रॉबिन।
प्रिएम्प्टिव शेड्यूलिंग है, ठीक है। तो इसमें क्या होता है कि एक फिक्स्ड टाइम क्वाटा होता है, वो हर प्रोसेस को ऐसे एक राउंड फैशन में हर किसी ये टाइम है, ठीक है। सो ये टाइम पहले प्रोसेस 1 को देगा, तो ये टाइम खत्म होने के बाद सीपीयू ले लेंगे, मतलब P1 रिलीज करे या ना रिलीज करे, शेड्यूलर इंटरप्ट करके सीपीयू ले लेंगे, उसके बाद P2 को दे देंगे। P2 अगेन इतना ही टाइम, ये फिक्स्ड टाइम है, हर किसी को सेम टाइम, सिमिलर टाइम दिया जाएगा हर प्रोसेस को। सो P2 एग्जीक्यूट करके ये टाइम क्वांटा खत्म होने पर सीपीयू उसे लेकर P2 से लेके P3 को दे देंगे। फिर P3 से ये खत्म होने पर P3 से लेकर P4 को दे देंगे, ऐसे 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 करते हैं। और
रैंडमली।
P4 नो ये एक फर्स्ट FCFS ऑर्डर में ही दे देते हैं।
एफसीएस फर्स्ट टाइम।
P9 सपोज P10 इतने प्रोसेस है हमारे क्यू में, P10 प्रोसेस है, तो P10 को देने के बाद फिर P1 को दे देंगे,
ओके
ऐसे राउंड फैशन में थोड़े थोड़े देर के लिए सबको थोड़ा थोड़ा दे देते हैं।
ओके।
दिस
रॉबिन,
राउंड फैशन,
राउंड रॉबिन।
राउंड रॉबिन, ओके। तो ये प्रीएम्प्टिव है, तो यहाँ पे सीपीयू इंटरप्ट करके ले लेते हैं प्रोसेस से।
ओके, यूनिक्स राउंड। थैंक यू।
और एक शेड्यूलिंग है बोलकर क्या है, शॉर्टेस्ट जॉब फर्स्ट, शॉर्टेस्ट जॉब फर्स्ट, हाँ SJF,
एससीएफ।
SJF शॉर्टेस्ट जॉब फर्स्ट। तो इसमें कैसा होता है कि जब भी प्रोसेस का बर्स्ट टाइम है ना, बर्स्ट टाइम के हिसाब से इनको पहले सॉर्ट करेंगे इंक्रीजिंग ऑर्डर में। मतलब अभी ये है ना बर्स्ट टाइम, तो इसमें इंक्रीजिंग ऑर्डर में सॉर्ट करेंगे, तो पहले 5 आएगा, फिर 10, फिर 20, फिर 30 एंड 60, राइट।
ओके।
P3, P1, P2, P4 एंड P5, तो इस ऑर्डर में एग्जीक्यूट किया जाएगा एसजेएफ में। जिसका बर्स्ट टाइम सबसे कम है पहले उस प्रोसेस को सीपीयू दिया जाएगा, देन वो प्रोसेस कंप्लीट होने के बाद द नेक्स्ट वन को दिया जाएगा।
ठीक, ओके मैम।
ये पेजिंग का कॉन्सेप्ट समझ आया?
यस मैम, अराउंड रोबिन टिप्स।
नहीं, मैं पेजिंग के बारे में पूछ रही थी,
नहीं मैम,
जो
वो
आज।
हाँ यस मैम, वो कंप्लीट इंग्लिश में तो मैम उसको रिकॉर्डिंग करके फिर से मैम पढ़ेंगे, ट्रांसलेट कर करके, और जो
ठीक है,
डाउट
ठीक है।
होगा नेक्स्ट नेक्स्ट सेशन में उसको पूछ लेंगे, रिकॉर्डिंग किए हैं।
हाँ, ठीक है, ठीक है। तो मेरा सेशन ट्यूसडे 6 to 8 है।
ओके मैम, ट्यूसडे 6 to 8, ओके मैम, नेक्स्ट टॉपिक में जो डाउट होगा पूछ लेंगे।
ठीक है, ठीक है।
उस पे मैम मेरा 2 असाइनमेंट मैं उस पे सबमिट नहीं किया, भूल गया था। कोई इशू मैम?
सबमिट ग्रेड पे मतलब सर्टिफिकेशन कर रहा है क्या?
मैम ग्रेड पे सर्टिफिकेट ना यूनिवर्सिटी से ये मिला, ऑपरेटिंग सिस्टम एनपीटीईएल वाला।
अच्छा, तो ग्रेड तो तुम लोग लास्ट एग्जाम भी दे देंगे ना सर्टिफिकेट के लिए, तो
अच्छा,
उसमें शायद अफेक्ट होगा। या यदि हम दो तरीके से टर्न कर सकते हैं, विदाउट सर्टिफिकेशन, ऐसे लेक्चर
अच्छा।
देख के सीखने के लिए, विद सर्टिफिकेशन के लिए असाइनमेंट सबमिशन और फाइनल एग्जाम जरूरी होता है।
12
तो
12 असाइनमेंट, 12
मुझे एग्जैक्टली पता नहीं है कि कितना इम्पैक्ट होगा, लेकिन इम्पैक्ट तो होगा सबमिट नहीं किया है तो। लेकिन हाउ मच इट विल इम्पैक्ट वो आई एम नॉट श्योर।
ओके मैम, बिकॉज मैम पहले से ये सब पता नहीं था, एक बार सर बोले कि तुम लोग का एग्जाम अब एनपीटीईएल पे होगा ऑनलाइन, तो पता चला कि तब तक 2 मैम छूट गया था।
ओके, ओके। अभी जो भी आगे अभी कल एक डेडलाइन है ना?
हाँ,
हाँ, वो विदाउट मिस ट्राई टू सबमिट दैट, एंड
यस
द
यस यस,
अपकमिंग वीक्स का भी ट्राई टू सबमिट एवरीथिंग।
राइट, यस मैम, यस मैम, फुल्ली किया मैम। ओके मैम, थैंक यू मैम।
या अंडरस्टूड। There are no more doubts, then we can close the session.
मैम इसमें असाइनमेंट में जो सर प्रोग्राम है वो समझ नहीं आता है, उसको मैम कैसे क्या करेंगे?
Problems?
यस मैम।
वो वो एक्चुअली इसीलिए मैं थोड़ा प्रॉब्लम्स करवा रहे थे, मतलब वो थोड़ा वो बिट का एक बार समझ आए ना तो फिर कर पाएंगे। तो
मैम
मैंने आज
सपोज,
5 एग्जाम्पल्स ट्राई किया था ना
अच्छा,
पेजिंग का। तो
हाँ
वो
पेजिंग का तो
स्टार्टिंग
देखा।
से, हाँ स्टार्टिंग से देख लो। वो थोड़ा इनिशियली जब हम देखते हैं तो थोड़ा कंफ्यूजिंग होता है। थोड़ा
ओके मैम,
ध्यान से एक बार वो बिट का मैनिपुलेशन, इसमें इतना बिट्स है तो कितना पेज नंबर पे जाएगा, कितना ऑफसेट या डी पे जाएगा, उसका ठीक से वो समझ लेंगे तो देन इट विल बी इजियर। फिर उसको मैप करना, फिजिकल एड्रेस में एफ और डी है, इसमें पी और डी है। तो एक लॉजिकल एड्रेस मतलब 32 बिट्स दिया है एंड यू आर पेज का साइज दिया है, तो उसमें से कैसे पेज नंबर्स, हाउ मेनी नंबर ऑफ, वो कैसे फिगर आउट करते हैं, वो एक्चुअली वो बिट के थ्रू ही फिगर आउट करते हैं। देख के वो एक बार समझ लेंगे तो हो जाएगा। मे बी एक बार और गो थ्रू करना वो एग्जाम्पल्स, समझ में आएंगे। और आई मीन इट्स लाइक सी, इट्स एज सिंपल लाइक, ये समझ में आया क्या? मतलब 2 बिट्स यूज कर रहा है तो हमारे पास 2 ऑप्शंस है।
यानी 4 options to
हाँ,
24. Yes, ma'am.
this concept you have understood, right? So if we have n bits, then we have 2 addresses or options. Okay. So ये n bits, if you are using n bits to address, like address में तुम्हारे address में n bits है, तो उसका ये क्या मतलब हो गया? You can generate 2 different addresses, right?
Yes, yes.
तो ये एक बेसिक चीज है, ये समझ ले। फिर देख लेना कि हाउ इज इट डन। हमारे पास लॉजिकल एड्रेस का, सपोज हमें बताया गया है कि 32 बिट्स है लॉजिकल एड्रेस, ठीक है? तो इसका क्या मतलब हो गया? 32 मतलब 2 power 32 डिफरेंट
Different
एड्रेसेस हो सकता है, ठीक है? यहाँ पे बता रहा है कि तो इसमें ये 32 बिट एड्रेस को हम कैसे पेजिंग में कैसे स्प्लिट करते हैं कि एक हो गया ऑफसेट और ये हो गया पेज नंबर। तो हम ये जो इसको डी बोलते हैं, डी बिट्स हम यूज करते हैं ऑफसेट के लिए, ठीक है? डी बिट्स आर यूज्ड फॉर ऑफसेट।
offsets.
तो इसका क्या मतलब हो गया? 2 power d डिफरेंट एड्रेसेस है,
Versus
2 power d
different
डिफरेंट एड्रेसेस है। मतलब पेज का साइज इक्वल टू पेज साइज इक्वल टू 2 power d,
2 power d. Yes.
ठीक है? तो पेज साइज, हाउ मच इज द पेज साइज? एक पेज का क्या साइज है? फॉर एग्जाम्पल 1 KB बताया है, 1 KB मतलब 2 power 10 हो गया, ठीक है? तो इसको रिप्रेजेंट करने के लिए हमें 10 बिट चाहिए होता है। तो ये डी हो गया 10, डी हो गया 10, पेज साइज हो गया 2 power 10। So this is how we retrieve the information. तो यदि पेज साइज दिया गया है तो 2 power 1 KB ऑफ मेमोरी है, मतलब 1 KB। तो हर एक बाइट को हमें एड्रेस करना है ना, तो टू एड्रेस एवरी सच बाइट 1 KB is the total memory, मतलब we have 1K bytes, मतलब 2 power 10 bytes है हमारे पास। So to address 2 power 10 bytes, we need 10 bits.
Okay.
ठीक है? तो इसे ऑफसेट हो गया एंड दिस ऑफसेट, ये पेज साइज इज सेम, पेज साइज यहाँ पे लॉजिकल एड्रेस स्पेस में और फिजिकल एड्रेस स्पेस में हम पेज साइज सेम रखता है, पेज साइज इज द सेम इन बोथ द प्लेसेस। तो यहाँ पर भी डी ही है। तो ये हो गया फ्रेम नंबर,
Frame और your ऑपरेंड नंबर।
ठीक है? तो ये एक बार इफ यू ये समझ आ गया ना, तो देन वो मैनिपुलेशन भी समझ में आ जाएंगे।
ओके।
ठीक है? तो अभी इस एग्जाम्पल में क्या हो गया? ये 10 हो गया, तो इसका क्या होगा? हाउ मेनी? ये 22 हो गया, राइट? पेज नंबर। सो हमारे पास 22 बिट्स है पेज नंबर को रिप्रेजेंट करने के लिए। तो कितने पेज नंबर्स को हम रिप्रेजेंट कर सकते हैं 22 बिट्स के थ्रू।
कितने बिट्स को रिप्रेजेंट कर सकते हैं
2
इसमें?
power 22 different pages, right? Different
Yes, ma'am.
pages, right? So total number of pages will be 2 power 22. 2 power 22 different pages we can identify using 22 bits. Okay. So this is how that ये बिट का एक बार समझ आएंगे ना, so then you will be able to understand it. Okay.
Okay, ma'am.
Yeah, chalo. Yeah, thank you.
Thank you.